Hi, good day everyone. I'm a lecturer, Dr. Fan speaking here, and today I'm very happy to share with you this topic under the atmosphere. It's called the ozone hole. So we all know that there's a hole in the ozone layer, but are we sure there's a blank there? Is it really a hole or is it something else here? And the ozone hole is always conveyed by scientists to politicians, to policymakers, to increase the severity of a hole in the atmosphere here. So this is my name and my office locations. You can drop me an email if you have any questions here. Okay? So the objective of today's class is mainly as such. First, we define what it means by ozone layer. How thin is the layer? How thick is the layer? Is it really a layer? Like a sheet of paper? Like a layer? Next, we evaluate if the ozone is good or bad. Right? Nothing is always good or just bad. Too much of something good is still very bad. Next, we define the ozone hole. What does it mean by a hole? And then we understand how the ozone destruction works by the different mechanisms. For one, it is a Chapman mechanism. Next, we try to understand what the famous Antarctica ozone hole really means. And then we evaluate the Montreal Protocol, the very famous Montreal Protocol, and what is the outcome. And then lastly, you understand the effects of the substitute gases on climate change, which is a very big thing. So first up, let's investigate the chemistry of the ozone. We have to know the structure of ozone, which is O3 here, with a triatomic molecule, O connected in a band manner in angular fashion, because oxygen comes from period 16 of the periodic table. It has got 6 electrons in its outermost shell, and when we bond them together using 2 sigma bond and 1 pi bond here, you will have a dative bond, and this undergoes resonance structure here to switch between the two species on the left and on the right here. You notice that we use this kind of arrow to depict this kind of canonical structures in organic chemistry in the Lewis structure here. And the reason why this takes a plus charge is that if we count around this central oxygen, the number of electrons that is closer to itself, we have 1, 2, 3, 4, 5. But as you know, oxygen has 6 electrons according to its Chalcodron series. So now it feels only 5. When it feels only 5 but originally has 6, of course it has, in a way, give up some of its electrons and therefore taking a slightly positive charge. And the same way goes for the other oxygen here that takes a negative charge. It has got 1, 2, 3, 4, 5, 6, and 7. Remember this line? 2 electrons sharing to form a covalent bond. Okay? So the bond angle is about 117 here because you have got the Vesper theory, right, which is the valence shell electron pair repulsion theory that talks about how the atoms will arrange themselves such that to minimize electron pair repulsion. In this case, you have got the lone pair and bond pair repulsion that is stronger than the bond pair repulsion here, right? So the bond length of this oxygen bond is on average 1.278 angstrom, right? My question for you is, why is this bond angle smaller than 120 degrees? Okay, which is a trigonal planar, right? Think about it, Vesper theory. So the ozone layer. So in the past lectures, we talked about different layers, right, in the atmosphere. So you have got the stratosphere, you've got exosphere that's high up, you've got the troposphere, right? And you see that the ozone layer is defined as, right, the amount of the O3 molecules, right, that resides, you know, in the stratospheric layer here, okay, which is a huge part of it. It does not mean that ozone only reside in the stratospheric layer, but somewhere else as well. But the highest concentration falls in the stratosphere. And this is where we regard our common term, the ozone layer. Okay, so the other 10% is distributed throughout the troposphere. So this stratospheric region, right, is called the ozone layer. Got it? Now let's do a recap. We have got different atmospheric layers, right? As I mentioned just now, the thermosphere, the mesosphere, the stratosphere, and the troposphere. And this is the part where you experience lots of weather forecast and climate that we see here. Not climate change, but climate that we see here, right? The rain, precipitation, snow. If you live in a tropical country like Singapore, this is less interesting. You've got the conventional rain, just dry, wet, humid. In high up space, you will see some rockets if you're nearby certain countries in the north, the mesosphere level. Not in Singapore though, we're pretty sheltered. Meteor is also not in this part of the world. But in the stratosphere, you can take a hot air balloon in places like Turkey that can bring that about 20 miles above sea level, right? And this is where you can really feel the ozone layer here, right? And if you take a plane, sometimes you see that there's a thin layer of cloud. Are they really clouds or are they ozone? Think about it, okay? So let's think about this philosophical question here. Are ozone good or bad? Are they lifesavers or life killers, right? And it's always about the location where you find, right? And we explain to you why. So in the next part, we talk about why are there good and bad ozone, right? And it's actually a very simple idea because ozone here, right, in the top layer, it absorbs UV, ultraviolet C ray, and some of the UVB rays. So it filters through this kind of ultraviolet rays that's very harmful potentially to human skin, causing some gene alterations and finally cancer here. So when it does a filtering role, it is good for us, okay, in the stratosphere. But the thing is, in the next tier, which is about 20 kilometers above sea level, it is bad. Because, right, ozone traps heat. Why does it trap heat? Remember the Lewis structure here? These bonds can vibrate like a spring here. So when it absorbs energy here, it traps heat. And when it traps heat, when it vibrates, it also releases heat. This ozone is a greenhouse gas. And in this part of the layer, it is bad because it warms our Earth. Now the next part here, it is good. Because, right, ozone, having a dative bond here, that bond is pretty weak here, but it does, react with some of the radicals and destroy pollutants because it reacts away to form oxygen gases, more O2 for us, for the organisms, and the oxygen can collide and react with some of the harmful radicals from these air pollutants, right? So it is good in the mid-tropospheric level. But again, it becomes bad again, right? When you have photochemical smog, right, that resides a bit lower to us here, like here is this region, it does cause some breathing difficulties, and it does cause some part of our biosphere as well in a negative way. So at first, ozone is a huge, giant ultraviolet screen here. It filters the harmful UV rays here, but remember, there are three kinds of ultraviolet rays: UVA, UVB, UVC, and these are governed by the wavelength of each of these band. Okay, so if you recall, the shorter the wavelength, the higher the frequency, right? The higher the frequency means the highest penetrating power, the most powerful, the most harmful. It can go deep to the skin. The shorter wavelength it will be UVC, and the longer wavelength is UVA, which is least harmful here, and our skin would not mind that. So that's a tanning effect. Okay for human, but again, too much of this is not good. But the UVB and UVC are really, really harmful and could be deleterious to our well-being. So we are happy that some of this ozone can filter the harmful UVC, right, and some UVB from us. UVA is hardly affected by ozone, and therefore we could put sunblock. As you have seen in the previous class here, I really applied sunblock. Okay. So this is the diagram of the solar flux, right, in terms of watts per centimeter square per nanometers here against the wavelength of the ultraviolet rays here, is to really illustrate, right, how penetrating this UV absorption is. Okay. Next, we ask ourselves, how is ozone being formed and how is it being destroyed naturally? When I say naturally, means there's no human interventions or any chemicals here. So primarily it's based on the Chapman cycle, and you have seen in our previous lecture that there's a steady state approximation to calculate the concentration of ozone actually, but we are not talking about physical chemistry, so we don't do in that. But you see that in the first step here, you have this photochemical reactions where you have a homolytic cleavage of the OO double bond, a sigma and a pi, to form two oxygen radical that stays in a transition fashion. Okay, and then this oxygen radical can combine with another molecule of oxygen gas and undergoes this equilibrium, a fast equilibrium exchange to form the ozone, and of course it's split, and then it goes back to the radical and O2, and it propagates here. Right, and we know that because to do a cleavage of the bond here, you need to have some energy, and that comes from the ultraviolet rays as well, with a wavelength of lower than 320 nanometers. So these oxygen molecules absorb high energy UV to break up into these oxygen radicals here, atoms, right, and then react slowly with ozone to form this, and you form O2. So you see like a cycle. It's a cycle because you use O2 first to form O, and O to react with O2 to form O3, and O3 reacts with O to form O2. So the final product in this Chapman cycle reactions here was the original reactant. It's a cycle. Okay? So radical. So I have a question here. Why must this wavelength be shorter than 242 nanometers? Right? And it's all because of the bond energy of O double bond here. That's about 498 kilojoules per mole. Now in the stratosphere, this UV radiation is the range of 200 to 320 nanometers that's being absorbed. So that corresponds to much of this ultraviolet C and some of this ultraviolet B. And we are thankful that this ozone in that stratosphere could filter these harmful rays from us. And the next part is about atmospheric cleansing, right? So what it does is at a certain level of the ozone here, they do good because it reacts with certain harmful molecules here, right? So you see that this table in the upper troposphere, right? The hydroxy radical, anything radical is not good for human because radicals attack our cells, right? So we have supplements called antioxidants. These are radical scavenger to eat them up, not to attack our cells. So likewise, in the atmosphere, there are radicals, and one of it is called the hydroxy radical, OH dot, and the dot is on the oxygen here. So this chemical compound are destroyed by the hydroxy radical, right? And to form that, we need to have ozone there. So you see that this NO itself is a radical. It reacts with in the process, right, in a sequential manner from stage 1 all the way to stage 6. From the ozone, right, it forms a O radical. O2 we care, okay, we don't need it. But the oxygen radical continues, right, undergoes a series of reactions here and eats up the harmful gases like NO, right, and then from the intermediates like OH, O2H, and subsequently it releases more OH dot, right, and then we destroy these harmful chemical compounds. If you want to read further, you can take a look at this part here. So we have this natural mechanism to clean the air. Okay, so just a little bit more. This is more inorganic chemistry when we have the O bracket 3P, right? So recall the single state, triplet state back in CM1111 or CM2111, right? This is about how the electrons are being arranged, paired, diamagnetic paramagnetism here. I won't go further in this class in the elective environmental chemistry module. But just so you know that, right, this D, it is a excited state, okay, and the P, triplet P, is the ground state. Next, we see a schematic diagram of the atmospheric cleansing by the ozone here. So as you have seen just now, the precursor always comes from O3, and then undergoing some photolysis, we split into O2 and O in the triplet state, and subsequent reactions here to continue with further reactions to form this hydroxy radical that eats up other chemicals like NO, right, to form NO2, and then this reacts with the rain to form HNO3. It's a secondary pollutant here. And how the rest of the chemicals in the atmosphere pertains to this picture you can self-read, right? And of course, this course is all pertaining to the connection between the hydrosphere, biosphere, lithosphere, right? And this ozone pertains primarily your biosphere and the hydrosphere. So see that this diagram, that the kinds of arrow, the kinds of bracket here tells you about the reactivity of certain radicals. Not all radicals are radical. What I mean is not all radicals have the same high energy here. Some radicals are a bit more stable, but it's still a radical. But some are very unstable. That means they might not even exist for a very short period of time. You just want to react away, like a ticking bomb. Excuse me. So some compounds like carbon monoxide with a CCO triple bond here, nitrous oxide, NOx, hydrocarbons, hydrogen sulfide, very smelly gas, ammonia, also very smelly. They are converted to CO2, H2O, nitric acid, and sulfuric acid in the process. Okay, and the types of reaction in this case, I hope you knew It is oxidation because it's a transfer of oxygen atoms, and of course it's a change in the oxidation state. So next part, we go deeper to the atmospheric cleansing by ozone. Right. So this table 2 shows the estimated amount of this global emission rate of tropospheric trace gases, right, in short TG, and the fractions of the absolute amount removed by this hydroxy radical in the atmosphere, right? So the mean global hydroxy radical concentration is taken as this amount here, 1 times 10 power 6, right, inverse centimeter cube. And we say TG is about trace gases is worth about a million of a million grams. Yeah. So you see a comparison that I will go through in the next lecture about the relative amount of these TG trace gases that's removed by the hydroxy radical, and this gives you an indication of how reactive these chemicals are, these TGs are, right, and the amount in terms of the rate of removal. Okay, so we want to read further for now. Just check out this journal, and I'll see you in the next class. Cheers.